Yeah, just walk out.
Walk out. Okay, so assuming that the recorder is going down there, for those that have to watch class later on, because you weren't here either this morning or you aren't here now, I just went over the homework assignment and the project. Both documents are posted. Just read through them in detail or ask your classmates about it. Okay, so moving on to the two formal instruction pieces for today. We're going to practice our computer numbering. And these will be the two sheets I want to work with. Okay, so if I were to convert between binary and ASCII, which is kind of the first thing I'm going to do, or the other direction, for these types of problems I need to create a little chart or a little table so that I can convert back and forth. So I'm going to start by writing down the placeholders, the numerical placeholders for the 8 bits in binary. So the first position is worth 1, 2, 4, 8, 16, 32, 64, and when I get to 128, I know I'm done. And then just as a sanity check, 1, 2, 3, 4, 5, 6, 7, 8. I've got the right number of bits, so now I'm ready to go. All right, so to go from binary to an ASCII character, I'm going to match up the numbers here with the places up there. So there's nothing in this first one related to 128, so I don't have to worry about that. There is something in the second position here, so that's going to be the number 64. So I'm just going to write over here 64, and then it's all zeros after that, and then second from the end there's a 1. So that's the 2. So basically in binary here I have a 64 and a 2. I add those things together and I get a 66. That's my number. And well, let me pull up an ASCII chart now. So, in decimal, the number 66 is what character? B. Okay. So, I'm going to write down in here the letter B. All right. Come back here. Okay, now I need to figure out what my next number is. There's something in the 64th place, so I'll do a 64. And then there's nothing for 32. The next one, I've got a 16, and I've got something in the 8th place, and then nothing, and then there's something in the last column, which is going to be a 1. So 6 plus 4 is 10, 18, 19, so I've got 89. And because I don't want to spoil the fun and have you guess what all the letters are going to be, let's go ahead and solve this last one as well. So again, I've got something that's in the 64 place, and then I have something in the 16 place, and I'm skipping again. So there's something in the 4 place and something in the 1. So we've got 6 plus 4 is 10, 15, 85. And with that, I can go over back to my chart. And for 89, what character is that? A Y. And for character 85? U. Yes. Show my school spirit. Okay. This one you get to do on your own. Your primary teacher appeared to you in a dream and gave you these 18 bits in succession. What was he or she trying to tell you in this dream? So go ahead and solve that. So there's your binary. Story behind it? Did you buy it online or like? And so you can Google ASCII chart to map the decimals to letters. Yeah, just Google ASCII chart. ASCII. Does anybody need more time? Okay. And so, what do the numbers end up being? 84, 82, and those characters on the ASCII chart are CTR. Nice. All right. So now let us throw some love out to Gary in our next problem. So it's actually a little bit harder going the other direction. It's not that bad, but you would start. I'm going to write this down again one more time. 128, 64, 32, 16, 8, 4, 2, 1. Okay, so if we're going to start from a character and then get all the way back to binary, here's how we would do it. First, I will look up the numbers. So capital G is a 71, and A is 65, R 82, and a Y is 89. Oops, sorry. God, tell me these things. Okay. Okay, so when we try to figure out what the binary is that goes with the number, we would start off with a number, so I'll write the number 71, and I'll look over here. Is there a 128 that's within that number? No, it's too big. Is there a 64 that's within that number? Yes, there is. So I will put a 1 right there, and then I'll write 64, and then 4 minus 11 is 7? 11 minus 4, sorry. Reading it upside down. Okay, so we have 7 left. So is there a 32 in there? No. Is there a 16 in there? No. Is there an 8 in there? No. Is there a 4? If I just add these up, 4, 2, and 1, that does make up a 7. So I'll just take all of those. 4, 2, 1, and that is my answer. So it's 0, 1, 0, 0, 0, 1, 1, 1. So I'll do the same thing with the number 65. Okay, is there a 128 in there? No. Is there a 64 in there? Yes. So I'll write down 64. I only have 1 left. That math is easier to do. And then, since there's only 1 left, and I know that comes at the end, I'll just do 1, 2, 3, 4, 5 zeros, and then another 1, it looks like. So that would come out as 0, 1, 1, 2, 3, 4, 5, 1. All right, and I will leave it to you to do the next two. Okay, does anybody need more time? Okay. So I probably don't need to go through the calc. Well, the last one, 89, that's a Y, so I already have that one up there. 0, 1, 0, 1, 1, 0, 0, 1. And then what does the binary work out to be for the R? 0, 1, 0, 1, 0, 0, 1, 0? Okay, sounds familiar. Excellent. Oh, it's on C. Ah, yeah. Well done. Okay. So we've been messing around with our bytes, so our 8-bit numbers. Now let's go down a little bit and work with nibbles. Nibbles have a nice even relationship with our hex characters, so whenever we're looking at our MAC addresses, and oftentimes in many places when we're packet sniffing, working with networking software, we'll see things in hex. So given 4 bits, if we just take this, so we've got 8, 4, 2, and 1, and if we have binary associated with that, for example, either of those, what is the smallest number and what is the biggest number that we can make based on only having 4 bits available? 0 to 15. Okay, so if you were going to solve some problem related to hex, I would start off with, and nibbles, I would start off by creating some type of chart like this one. So you can just write out 0 through 15. You write out 0 through 9. Once you get to 10, you write A, B, C, D, E, F. Okay, so for this binary right there, that's 8 plus 4 plus 2 plus 1. The decimal there is 15. And in hex, that's an F. The next one is all zeros, and all zeros comes out to 0. And I'll leave it to you to solve the next two. You're supposed to have class tomorrow, correct? Is anybody going to Silicon Slopes? On Friday. Is anybody going to Silicon Slopes on Thursday? You are? Very responsible of the rest of you. So, you guys are invited to ride the train with me up tomorrow if you want. I'm going to go up in the morning, but before extending that invitation, I realized, oh yeah, you guys have classes. So, anyway, I'll probably go up on Friday as well. I'll be taking the front runner again that day. Okay, so you got it? Anybody need more time? Okay, so this one has an 8 and a 1 represented, so that's 9. And 9 on our lower row here is 9. All right, and then so this one has over here an 8 and a 2, which represents 10. And then 10 in our little chart here is what? The letter A. Woohoo! Okay, next task. This is the MAC address, the Mac's MAC address, technically. My Macintosh's media access control address, written right there. And so I'd like you to first turn it into decimal, and then turn it into binary. And if you're typing into a Word document, it should expand. Otherwise, just write it anywhere, however you want.
What do you mean by converting it to the decimal?
Well, so for example, a C, yeah. When I say I say it that way because when you read the ASCII charts, whenever they list just the whole numbers, they call it the decimal column.
And then are the numbers just themselves?
Yeah, exactly. So we'd actually just jump back to the previous page for the C, which is 12. Yes?
Is this going in a binary or nibbles or whatever it's called?
For each of these characters, you would only need 4 bits.
Yeah.
Yeah, so just make them nibbles. Nibbles rather than bytes. Yes,
So, when we bring this binary, there's just one, you typically put 3 zeros and then the 1, or just keep it 1? Like the 0, is it 4 zeros?
Well, okay, so you can either do a nibble or a whole byte. So I think that's what you're asking.
Yeah.
If-
Or can
yeah.
you just leave it as like 1?
In this case, what I'm thinking is just represent them as nibbles, and so just do, yeah, and if there's nothing there, if the number is like 1, it's gonna be 0001. And I guess if it's 0 in the middle there, that'd just be 4 zeros for this exercise. All right, that's enough of that, even if you haven't finished. So, how many of you have seen the movie UHF? Right. I'm going to play a clip from that right now. Let's jump over to that. This is going to relate to our discussion of local area networks and Ethernet. And it just so happens whenever I play one of these clips in class and then I upload it to YouTube, the copyright police come after me and they say, you just uploaded a video of something that's copyrighted, so go out and buy the movie. Anybody goes and checks on this. Not you guys, YouTube. Okay, so. So I want to focus, so you got Weird Al Yankovic, and then you've got Kramer from Seinfeld.
Listen, just stall as long as you can. I'm sure I'll try.
The emphasis here is going to be
100%.
Kramer.
They're doing everything they can.
Also Stanley the
George
janitor,
Fletcher's behind this. I just know it.
who has been kidnapped.
Okay, I'm thinking of something orange. Something orange. Orange. You give up? It's an orange. Get it? It's fun, huh? Okay, now I'm thinking of something blue. Something blue.
Let me kill him. Please, let me kill him. Dun 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 dun. Dun 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 dun. Dun 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 dun. Hey!
What? What?
Oh.
Okay, all right. It says, what is the point? Okay, that's a good question. I have an answer. I do have an answer. So, wrong side. When we talk about local area networks, the big issue with them, okay, when we talk about this, obviously when you do your readings and when we go over these slides, there can seem to be a lot of details to it. But if I could have you just take one thing away from a manager's perspective, the key issue with local area networks is congestion. That every device is like Stanley the janitor that gets on a network. They're really, really chatty. And when we open up Wireshark in a little bit, we're going to see how chatty every single device, every phone, every computer, every Raspberry Pi that gets on a network, how chatty they are. And so as we get too many devices on a network, eventually what happens is either everything slows down as they're competing for limited bandwidth, or it completely stops as errors occur. So just from a managerial perspective, a local area network manager's job, or key job, is going to be to make sure that we have enough flow through our network, and too much chatter is going to become a problem for that. So a lot of the things that we're talking about are going to ultimately get back to this issue. How can we control congestion? So, okay, with that, let me go back to the beginning of things. So everybody in our network is a Stanley. Okay, so our local area networks. This guy wanted to get on, have local networks that could access the big superhighway created by DARPA, or early Ethernet, and it was meant for small groups. And we talked about how you can send out a message under original Ethernet and everybody sees it. And so when you see something that's not destined for you or not intended for you, you just ignore it. We talked about how do you know that something is for you, and that is that on every piece of physical networking hardware, there is an address burned into it that's recognized, our media access control address, or physical address. We looked them up, and we talked about how every device has a MAC address associated with it, or better yet, the network interfaces have them. And then we left off talking about how that address has 12 characters in it, and that physical address, and the first 6 characters relate to an organizational identifier, and the last 6 characters are a unique identifier to your specific interface card. So here's a little activity we can do. Let's go to Google and type MAC address lookup. So if I type in MAC address lookup, and I go to the first link there, here's a form where we can type in the first 6 characters. So for my Macintosh that I'm on right now, my characters are 8C8590, and I'll do my Raspberry Pi in just a second. You guys are also welcome to do an IP config, look at the physical address of your machine, and type in the first 6 characters on there.
Wait, how did you find that?
How do I know that? If I am on a Mac, or any Unix compatible machine, I type in ifconfig from the terminal, and somewhere in there it'll say ether, like that. And so I'm looking for the first 6 characters. This particular thing has a lot of connections, but one of the earlier ones is going to be 8C8590. Right there it says 80, or right there where it says ether. You would type in ipconfig if you're on a PC and you opened up PowerShell or the command window. So I type that in, I click look up MAC address, and over here it says the creator of that hardware is Apple. Similarly, if I were to go over to my Raspberry Pi, and if I type in ifconfig over here, I see its Ethernet address, and its first characters are DCA632.
Oh, yeah.
DCA632. And after we look it up, it recognizes those characters as being associated with Raspberry Pi hardware. Yes.
So does that first 6 digits, does that change ever per company? So Dell, if it's a Dell computer, it's always going to have those first 6?
Yeah. So okay, so I'm going to expand out your question a little bit, because it leads into something related. So I believe that Raspberry Pi is always going to own that address, but here's the deal. I don't know what the number of permutations is for the last 6 characters, but let's just say that you could have 1 million unique identifiers with that company and then the last 6 characters. That means that after they've done 1 million Raspberry Pis, then they have to start repeating again. So one of the options they have, and this is what happens in practice, is for a company like Apple, they have lots of these prefixes that are assigned to them. So there are some websites you can go to where it's just page after page of Intel or Apple prefixes that they're allowed to use. And then for each one of those prefixes, they can cycle through millions of unique IDs. So in practice, in theory, you should never get 2 network physical addresses that are the same. In practice, it is possible. It's very unlikely you're going to get 2 people in the same room that have it. But it is possible, yeah.
What happens if you run out of the MAC addresses, for companies and
Well, let's just say it's 1 to a million for those last 6 characters. They just start over again, or they just go over to one of their other prefixes, and then so maybe they've got.
The prefixes themselves.
They have a limited number of prefixes that are assigned out there. So basically they've got their prefixes, and then for every one of those prefixes they can do millions of cards, so they can just,
Okay.
millions of IDs, they can just cycle through those as however they want. Yeah, so if they ran out, they have to repeat.
Okay.
Ultimately is what happens. So if you're a small shop, they might assign you a unique set of characters, but they probably won't give you lots and lots of prefixes like Intel or Apple does until you're a big time player. All right, fun. Alrighty, so just like there's 3 types of toilet paper hangers in this world, recently I've done both of those. My wife does this one, it drives me crazy. So the original patent shows very clearly that it's this and not that. It's all over Facebook, everybody knows this. But anyway, so there are 3 types of MAC. So right now the way it's been presented is that every single MAC address, like this one, is unique to a device, but there are other uses of MAC addresses. Let me drop down to the bottom right here. So sometimes if we're sniffing network traffic, what we will see is a series of Fs instead of an address like this. This, in nibbles, turns into all ones. So when you see all ones, that's a broadcast message. And it just so happens that all of our devices are regularly sending out broadcast messages all the time. So just like Stanley doing the Bonanza theme, it's always anyway. They're constantly sending out broadcast messages which are meant for every single device on the local area network. And so that's where part of the congestion comes from. The more devices you get, the more devices that are always broadcasting to everybody else all the time as part of their kind of status check, system maintenance kind of activities. This next one right here is kind of like, what if you had a broadcast that wasn't for everybody in the network, but just for some groups in the network? There's a hyphen here, which means there's a range. So we could translate this into something. I don't know how many unique addresses exist within this range, but let's just say that there's, I don't know, thousands of unique addresses that exist within this range. What you're allowed to do is, as a group of people, you can say, I also subscribe to one of these addresses in this range, and then you can get a broad, so then from like the switch's perspective, it can send that exact same message to all of you at the same time, but unlike this one, only some of you get it and not everybody in the whole room. So when does this come into play? Well, let's just say you're watching General Conference. If I am the sender of General Conference and I'm broadcasting to this room, it would be inefficient for me to create 72 separate streams from the source. So instead, I create one stream that goes down to your switch, and then the switch just multiplies to everybody that's registered for that broadcast. So it's kind of like you have 2 addresses. You have your regular address, and you can sign up for a second one temporarily, saying, hey, I want to get this broadcast, this multicast message, which is only going to go to some of us in this room, but maybe not others. Another way that this is used is when I image computers in the lab. What happens is I start off with a PC that has a version of Windows 10 on there that I want to push out to everywhere. It's got a bunch of software on there, Visual Studio, all kinds of different things. And it's about 30 gigs in size when all is said and done. And I need to push it out to 32 stations in the room. So when I press go, one of the things so there's 2 ways I can do it. If I don't do multicast, then it tries to create 32 separate streams upon which it's sending out 30 gigs on each one. And each one is doing it kind of at a different rate. And once it gets to 2 or 3 computers on the network, the machine poops out on me. It says, I can't put out that amount of bandwidth, I can't process that amount of information, 30 gigs, 32 different directions. But if I turn on multicast, then all of the devices on the back end, they're all listening, and it's just more. And then from the sender's perspective, it's just sending out one copy of the 30 gigs, and then when it hits the switch, it's just being copied to everybody else across the wire. So everybody's getting kind of the same message, but it's only being sent out one time rather than 32 times simultaneously. So, so in terms of what you should care about, yeah, you should care about this first one that, hey, every device has a unique address. You should care about this last one that all F's is special. It means it goes to everybody in the room. And then just kind of as a fun fact, you can know that, oh, there's a way to kind of subdivide my broadcast so that not everybody in the room gets it. Don't need to go deeper than that. Okay. There was lots of questions on that last time, but you don't have any, that's fine. Yep.
Is there a way I can do that with like my home router so that my stuff gets like quicker internet, or does that not affect it?
Well, I'm not sure. I'm not sure how that would work on a local network. So, yeah. Okay. So, how can we, now that we've learned about MAC addresses and the 3 types of them, how might we use this? Well, one thing we can do is we can keep track of kind of the digital footprint of the MAC address of every device in our network and control what traffic it gets or doesn't get. As an example of that, at my house, I use a device called the Disney Circle. Well, it might be up there. Okay. So the Disney Circle is a device that will configure itself to be between my wireless router and the physical devices. So everybody has to pass through that man in the middle, that device right there. And then the software right here, what it allows me to do is associate everybody's computer and every network device in my house to a picture. So if it's my son, I can get any computers or phones he has and associate it with an icon. If it's my daughter's, same kind of deal. I even do things based on rooms in the house, like the television. I'll give it its own icon. And the functionality this thing gives me is I can pause any particular place in the house or any user in the house, like when my kids would get grounded and they need to do their homework, they get paused. Another thing you can do is you can filter the type of traffic that they're allowed to get. So if your son is up in the middle of the night in a dark room, looking at things he shouldn't be, like University of Utah website, then what we can do is we can restrict any kind of traffic that they get, or we can monitor that. How does this all work? Well, it's because of the MAC addresses. That's how we uniquely identify everybody's device. You saw on a previous day, I had the little consumer Linksys wireless G router sitting on there. Those devices, you can log into them, and it'll give you a list of all of the MAC addresses of devices that are connected to your network currently, and then you can set rules and profiles for each of those addresses. If you want, and you can do this for your roommates as well. You could say, if you knew how to get onto your router, potentially you can say, hey, this person only gets internet between this hour and this hour, or they get 2 hours a day, or whatever. You can do all kinds of fun things to mess with people if you know the MAC address of their device. Yeah, David.
So obviously, we were talking about before, it's an important thing, especially for parents and keeping their kids safe online, but just in a real sense, they've got data as well. And as a parent, what do you do for that?
Wait, in a real sense, they...
I mean, if your kid's looking at University of Utah stuff,
Yeah.
and, he just goes to his data instead of just turns his Wi-Fi off.
Yeah, so, well, you can, they also have companion programs for this kind of thing where it'll be, that you can install on the phones as well. So it's not going to use the Wi-Fi network at your house, but the same program can sit on top of your cellular data plan on any of your mobile devices. So you just need to have the password, the administrative password to any phone. You install it on there, and then you're blocking them and controlling them there just as well. So, yeah, that is on a serious note a big issue is trying to deal with technology with kids and things that are not appropriate, and it becomes a big battle. It's hard. Okay, yeah.
Is there a way to find someone's MAC address without going on their computer? Can you do it through the network?
Oh yeah. I mean, you just like my sister, she'll come over and visit my house, and I'll just look in my router and I'll look at the new MAC address in there. I'm like, everything else is associated with something in my house except for that one. I'm like, oh, that's my sister's iPhone. So. Pardon?
So it's time to shut off our internet.
Yeah, I don't think my sister would appreciate that. She might not visit me anymore.
So you said you can spoof your MAC address, like so if you're on like, so you know how Xfinity has like free Wi-Fi everywhere through the router or whatever?
Yeah.
If you were to use someone's MAC address that's associated with, I guess.
So, all right, so on that one, I just kind of thought about it and I made it up. I'm software-wise, there shouldn't be any reason why you couldn't spoof a MAC address. But the other item I put on there is, I said on there well, actually, I'll put it to you this way. How might the fact that you have a MAC address associated with every single packet that you send relate to security and forensics? I'm talking about Wells class. How might that relate? What is the security implication of having MAC addresses? Yeah.
I'm just thinking, like, if you knew the MAC address, you can see, like, where it's coming from, like, if it's an app computer, or, like, what kind of processor it has, and if you were, like, manipulating software, it would be simpler to identify.
I would stop with just, you can see where it came from. So if you have a record or a log of your network traffic, which you can enable even on your home routers, you can enable that logging. And if there's some type of investigation, there's no way that two packets could be exchanged or a packet could be exchanged between two devices on a LAN without a source address and a destination address. So you know the device definitively that collected data that should not have, gone over to a particular device. So cool stuff. Other questions? Yeah.
Is the MAC address used at all in Bluetooth, or is it Bluetooth?
Yeah.
different?
Well, yeah, Bluetooth has an address as well. So just off the top of my head, I haven't just verified that, but I'm pretty sure, even just looking at my Mac as I do the little listing there, it's got an address as well. Let's see if we can see it. So here's, sorry, it's a little small. One of these should be my Bluetooth. I don't know which one it is, but I'm pretty sure that your Bluetooth will have a MAC address as well. I know I've looked at it before, I just don't know off the top of my head. But I think the answer is yes.
It's a separate address, though.
Probably, because, and you see a bunch of different listings here based on the indentation. So everything that connects to a network is kind of its own network interface with its own address. In a broader scope, if I have a PC, I can put in 10 different network cards in there, and then when I do this IP config, I see all of them with a different entry, all of them with a different physical address. As we add in Wi-Fi antennas, as we add in Bluetooth, each of those should be getting their own unique identifier as well that's shown in this list. Yeah?
So with forensics, if an attacker used like VPN to track how a MAC address is playing,
You're probably, you'll have to ask Wells, but I think you're in trouble at that point, because if you're coming in from an outside device, and then you VPN into a particular machine, any traffic that leaves that machine to the rest of the network should be recognized as the physical address of the VPN machine that you're logged into. So all the traffic's coming from there. There may be extra stuff that goes along with that. Maybe it invents or spoofs some addresses for using, I don't know, but as a starting point, it would be a problem. Yeah.
It's kind of related to the Disney app, but I found a thing last week where you can turn your Raspberry Pi into like a universal ad block for your entire house.
Oh yes, Pihole.
Yeah. So you can plug it in, like block YouTube ads, and you can also like block your roommates and stuff too.
Yeah. That's a super cool. That's one of the cool programs with your Raspberry Pis. You can install some software called Pihole, and then have all of your networking go through your Pi, and it knows all the sources of where ads are coming from. And it has like a blacklist, and so it just doesn't allow that traffic to come through, and therefore all of your internet browsing is faster because there's a lot of traffic that never comes in. Mitchell.
I was going to say, it is like surprising how much faster my internet was after implementing that. I didn't think it would make that much of a difference, but like
Really?
I've been doing speed tests and I was just kind of like, oh, this is unexpected. YouTube ads though, you have to actually find the IPs because they're usually coming from a similar source as the actual video, and so those do not come immediately with the file.
Awesome. We're learning how to be such great hackers as part of this class, hacking our lives. I like it. Any other questions questions related to that? Okay, next topic. We've been talking about addresses on the physical layer. We just talked about 3 classes of them. But we've been also talking about, we've also kind of in the background talked about delivering packets. So the addresses are something that sit on packets. But what is your packet exactly as it relates to Ethernet? Well, we can think of an Ethernet packet as an envelope. It's something that has a source address and a destination address, and then inside it has a payload. Typically the size of an envelope, or in terms of bytes, is 1,522 on the high end, in terms of an uninterrupted sequence of ones and zeros. Another thing this brings up is when we start talking about what is being shipped around, we need to be more precise with our terminology. Oftentimes we say packet, but there's actually different types of packets. So depending on which layer of the OSI model we're talking about, let me start from the top. So let me go above data here. Let's imagine that this is a web server represented, and it needs to return a web page. So the web page itself, the HTML page, is just data. It's characters. So for through the first 3 layers there, it's just data. Then we take this information and we maybe separate it into a couple of different blocks. Maybe we need to send it in 2 parts or 2 packets to the user. So we call those segments, and we put like number 1 and number 2 on the 2 segments. But we need some more information. So now it's in 2 parts. It's just data in package 1 and package 2. But we also now need to send it over a network using internet protocol. And with that, when we add in a little bit of information, which is the source and the destination IP address onto it, now it's called a packet at the network layer, or the IP layer. But if we're down on the Ethernet layer, then we need to add one more thing, which is our source and our destination address for Ethernet. And the packet at that point is called a frame. So once we've added in all the different kind of like packages and stamps to it and bundled it all up, then it's called a frame. And now we're ready to turn it into ones and zeros and send it around send it around our local area network. I have some ways to visualize this. So if this over here is our original data, we just added some headers, some additional ones and zeros at the transport layer, again at the IP layer, and then lastly at the Ethernet layer, which is going to add in our source and destination physical addresses. Then it's turned into a bunch of ones and zeros, sent over a physical medium, and then when it gets to the other side, we kind of unwrap the process. We strip off the Ethernet package information, we strip off the IP information, we strip off the transport information, and then we have just data. So we might think of it like this, like Russian stacking dolls. We have data that we put into a segment, which we put into a packet, which we put into a frame, and when all is said and done, the frame is the biggest unit that we have that we're passing around. Yeah?
How does the computer differentiate between like addresses and information? Like if it's all ones and zeros going through constantly, how does it like the breakpoint? Okay, now I'm reading my information. Here's my head. Like, is it just the?
Yeah. No, I know what you're asking. And as I'm pausing to think, I'm going to stop class potentially a little early today, depending on, I don't know, we'll see how things go. No, but we are absolutely going to get to that. We're going to get to that next time. But just as a preview, at the Ethernet layer, there's a prescribed format for the packets. There's a series of bits, patterns, that is the synchronization sequence. So if I'm some device, any device listening on the network, when I see that synchronization series, I'm like, aha. I know what's going to happen at the end of this 64 bits or whatever. I'm about to start an Ethernet frame. And so as soon as that synchronization sequence is over, I'm like, here's the beginning, and then there's a certain number of bits that go by, and then there's another sequence that shuts it off. And then so we just get a whole bunch of those in a row. So in a sense, it's sort of like a river. It is kind of a problem for devices. Like, how do you know if you just jump onto a network, what's the start and stop to all the communication? You listen for the communication sequence, then you're caught up. And then, kind of like buffering or something with when you're watching Netflix. Like, okay, now I can just watch everything in real time, and I know what it is based on the markers at the beginning and the end of each packet.
Okay.
Okay, so you have hopefully opened up your Raspberry Pi, and let's mess with it. So you've run those commands. If you have Wireshark available on your desktop, that's fine as well. All right, so yeah, it doesn't matter. Okay, I've already installed stuff, so I'm going to type in sudo Wireshark. All right, and so as I do this, a very pleasing thing happens. It looks like little heartbeats, like little heartbeat monitors at the hospital are happening right there. That's network traffic on 3 different network interfaces. So the traffic, so in my house, I actually have my Pi connected to my router, both through a physical Ethernet cable and through my wireless antenna that's built into the Pi. So both of those are talking to my router. Traffic can go over both of those network interfaces. Okay, so let me, so as soon as I double click on this, it is going to start recording packets or frames of information flowing by. Okay, so there we go. Right now it's doing the Stanley thing that I was telling you about. I'm going to hit stop. Okay, so in just a couple of seconds, I have captured 1,078 frames. So typically of that size, we can actually see the length there. On the higher end, it looks like I've got some 1,514 bytes. Looks like some of the packets that are flowing by, some of the frames flowing by, are actually smaller than that. But that is quite a lot of them. Okay, so the first window here shows me on the left-hand side the sequence number, so just ordered for the frames that are coming in that it's viewing. If I go down to this second window here, depending on the type of information that's been received in that packet, I see it, here's kind of like the Russian doll sequence. So we have a frame and an Ethernet packet, which is really, generally speaking, it's kind of the same thing. So we have the Ethernet frame right there. If I open up the second thing, which is my Ethernet packet / frame, there's a couple things that I think are interesting to point out. So remember, with your Ethernet frame, you have a source and a destination for the physical address for everything that's being sent around. So right here I see, for this particular thing, it says the source. Let's see, the source is from Google. Well, it says Google, and then it's got some more characters. This is actually, well, what this is my Google Fiber router that's in the house, the access point. So my Google appliance has this physical address, and kind of like I was showing you before with the organizational lookup, that you can do the MAC address lookup, it actually took those first characters and over here replaced it with the word Google, and then the remaining characters at the end stayed the same. So that's kind of the unique identifier. So this is the same thing in both places. And the same thing with the destination. So this is a packet that was sent to my Raspberry Pi in this particular case. So it's working in both directions all the time. There's frames coming to my device and frames going out from my device. In this particular moment, I have as the recipient, the Raspberry Pi. This is my Raspberry Pi's physical ID, and then if we take those first few characters and change it to its organizational identifier, it comes out like that. So that is as far as I got with the other class, and so I wanted to stop there with your permission. Is that okay with you? Okay, so you got an extra 4 minutes.
Question.
Yeah.
Just with like the MAC address, like on your own, on your PC, like I did like the config or IP.
IP config, uh-huh.
Like where do you find your address? 'Cause I like didn't see one that looked like that.
Did you use your git bash or command prompt?
Yeah.
So I couldn't do it on git bash, but I did it on command prompt, that worked.
I did not know that, but that's good to know.
Yeah, you just do, you go to command prompt and do IP config, and then you have to do /all. Maybe that's.
Okay, so maybe git bash may or may not work, but the command prompt should. Yeah, but IP config, I think like an all switch potentially will show more information. Other questions? Yeah, Jacob.
Is your Raspberry Pi, does it show that it's going to the circle thing, like do this?
I don't actually have the circle turned on right now. Yep. I was afraid it was slowing down my network. And the kid who never would do their homework moved out of the house and is, yeah. So I'm not worried about them right now. So, all right, have a good day.